Okay, it's time to begin Unit 16E, which is about waves. And we begin with the types of waves you can have. And I've got my little wave generator here, otherwise known as a slinky. You can have a wave that's just a pulse, travels along. And, so it's something like this. It's maybe moving along that way. Or you can have a sinusoidal wave, which can look something like this. Right? Keeps going back and forth. And so it's got a sinusoidal thing and everything moves along. All parts of the sinusoid drive along, and of course new ones being created over here that's going to come in later, and the old ones go out the other side. Same with the pulse. The other way to think of it as splitting waves up is transverse. And the waves I was just showing you are transverse. They go off to the side. The displacement is perpendicular to the velocity. And so you have this, and the corresponding other one is called longitudinal. And the reason why I use this is you can make this kind as well. If I take and give a little push in and out, you see that dark spot moves across the I have a thicker spot that moves across the screen here, which is, I do it enough times, you might be able to see it. And so what you have is a part that's apart, and then the part that's connect together, and then the part that's apart, and the part that's together, and so on. So you have squeezed, stretch, squeeze, stretch. And so and of course the squeezed parts here, the stretched parts move along, the squeezed parts move along, the stretched parts move along, the squeezed parts move along, back and forth, and this is moving too, presumably. And so here the displacement which is the motion of the spring, right? The motion of the spring here is perpendicular, so motion, which is displacement, and velocity. In this case, the displacement is this way, right? Close together, further apart, close together, further apart. And the velocity is that way. So they're parallel or anti-parallel to each other. And so these squeezed regions are sort of, you can picture the squeezed regions as sort of traveling along with the velocity down through the material. And then the other thing we can look at is reflection of a wave. And this actually depends on what you have. Suppose I hold this side tight. And then watch what happens. I go this way on the way in, and it comes back this way. It goes in like this, and it comes back down like that. It looks like it's going around in a circle almost, right? Because it comes back inverted. And so if I hold this end tight, and it's going in. Then after reflection, it's going back out. It's inverted. So hold tight. The reflection is inverted. And if I go the other way, of course, if I start down here, then it comes back going up. Now, if I have free motion, so you can imagine this is free to slip. In both these cases, then this one's going in. Let's see what it looks like. Now it's hard to get it really free to move. So what I'm going to do is I'm going to hold it in the other end of this little spring here so that it can sort of move freely here. And if I send this in, if you look carefully, you'll see, well, it's still on the top. Oops, really on the top that time. So as I hold this in, it comes back and it doesn't come down here. If you look at this, nothing goes below here. It goes in and then it stays in the top, goes in like this, comes back like that. And so it comes back not inverted. And so free end, not inverted. And the way to think about it, of course, is that there's a force here. That inverts it. Whereas over here, no force, no invert. This will become important later when we start looking at how things manage to interfere with each other. If we keep sending them in at a constant rate and they bounce back, they're going to start adding up to something strange. But before we get there, let me just pop you over to this. Okay, so I demonstrated both types, so you can consider either one to be correct, but remember, which was which? Run that through your head a little bit as we're thinking here. Okay, so the two basic types of transverse wave motion, that's the motion of the stuff that the wave is propagating along, be it a string or a spring or a slinky or air motion, whatever it is, or light motion. It's transverse if it's perpendicular to the wave's propagation and it's parallel to the direction in the motion of the material, then you call it longitudinal. It turns out that when I sort of pushed the slinky in and made that longitudinal wave, you can do it in a spring. Pretty hard to do that in a string, but the spring or the slinky, it's easier. I can move the transverse wave in a spring or a slinky. Light turns out to be a wave that's transverse. Most of the motion of a rope, if you show it sideways or spring, those are transverse. Longitudinal waves, sound is the most common. What you hear when you hear my voice is sound. That's a longitudinal wave. The air is compressed together and pushed apart, compressed together and pushed apart. And that compression of the air is the restoring force. On the spring, it's how hard I'm pulling against it gives me the restoring force. I actually have to pay attention to it. That gives me the restoring force. So here's a question. It's not really a clicker question. A wave is transmitted along two strings that are identical except one is pulled tighter than the other one. How do the speeds compare? Well, the speed of a wave is actually given by, for a wave on a string, is given by the square root of the tension divided by the mass per length. Now notice we have to say mass per length, because it doesn't depend on how long the string is, it just depends on what the tension is. And the reason why that's the case, of course, is the fact that speed has to go as the force that's restoring it divided by the inertia, just like we saw for the frequencies. And the restoring force is tension related to it, and the inertia part is the mass per length. And so when you have one pulled tighter, then you have a higher wave speed. So the A is the answer right there. Now we go through air or helium. Which medium is the wave speed faster? Again, you think of this idea as, what's the restoring force? Pressure. Okay, if it's, we're assuming that the two have the same pressure, so it's a really comparable thing. And the other thing you look at is inertia. So which is heavier per molecule, air or helium? Well, you ought to know this from chemistry. Air is mostly nitrogen and oxygen with masses of atomic masses of 14 or 16, double that for what they are in the molecules in air. Helium has got a mass of 4 typically, sometimes 3, and it's by itself, so it's much lighter weight. So helium has a lighter weight, that's on the bottom, so that means it goes faster. Wave speed depends only on the material properties. And so you have elastic properties of it, which just gives you restoring force, and you have inertial properties, which gives you the, given by the density, really, usually. If you have a 1D thing, it's mass per length. If you have 3D, it's mass per volume. If you have something that's 2D, it's mass per area, right? That's the inertial part. The elastic part is the one that gets the units, right, that goes along with it. Now, usually what we're going to find is that the wave speed in a solid is faster than that in a liquid, is faster than that in the gas, because the restoring force is faster and is stronger in a solid. Solids held together by atomic bonds. It's really strong, you know, big, fast wave speed simply because you have so much more force. Whereas in a gas, the restoring force is just pressure, and that's not nearly as strong. So you can keep that in mind as well. And so let's go to this question. Iron bars hit with a hammer, you get a sound wave in the bar. And also one in the air, right? Because you hit the thing with a hammer, you hear it. But there's also sound that's going to travel right through that bar. So now you can listen on the other end and see what you hear first. And what you're going to hear first is is what comes through the metal bar, and then you're going to hear what comes through the air, because the metal bar is those, you know, solid bonds which are making the wave speed much faster. Also transmits sound a little bit better than the air. It tends to spread out in the air, but if you have a metal bar, it all kinds of goes right down the bar, which is why you hear stories about people listening to the rails and the railroad track to hear a train coming. Well, probably not good to put your head down where the train goes. The train's pretty heavy, but it would get there faster than it does through the air, nevertheless. And now, again, we go back to the same thing, elastic inertial properties, and we sort of gave you one another, and here's what I told you before. Okay, two tuning forks are struck. One gives us a high frequency, one gives us a low frequency. Which of these travels faster through the air? High frequency, low frequency, or the same speed? And the answer is, of course, back to what we said before. The speed of sound depends on the properties of the medium. So it doesn't matter what the property of the source is. It doesn't matter what the frequency is, only what the medium is. And so they propagate at the same speed. Now, sometimes medium properties of medium changes with frequency, but for the most part, not very much. So we're going to ignore that in this class. This is a go-to equation. Don't forget this. The speed of a wave is equal to its frequency times its wavelength. Now, you've heard about these quantities before. Frequency, we've been studying a lot with oscillations. Wavelength is more or less the equivalent of period, but in space rather than in time. And so this could be lambda or a period, and then you'd have both of them sort of things you'd pick off that graph of peak to peak or trough to trough. In time plot is period, in a distance plot is the wavelength. Multiply those together, you get the speed. And this is really comes out to whatever it is that you, the fact that you're creating a source of waves, right? And it's traveling at a certain speed, and you have to kind of get, each time you have one frequency, you've got to get the thing to move out one wavelength, otherwise it just doesn't work. That's what this is trying to tell you. But it turns out to be an extremely useful relation that you'll go back to again and again and again. And I'll sketch out pictures of what I just talked about on the notes I post. So wave speed is determined only by the properties of the medium. Frequency is only by the source. And the wavelength is just what you get. So remember that. Frequency depends on the source, because what the source controls is how often it goes up and down. Wave speed is in the medium only, and so you put a certain frequency into a certain medium, you're going to get a wavelength. You put that frequency into another medium, you'll get a different wavelength. And we'll give you a few equations to enforce this as it goes on, as we go on. So let's do an example of this. We've got earthquake shakes the ground at 10 hertz. 10 hertz is a frequency, and produces seismic waves. As they pass through solid rock, they have a wavelength of 400 meters. How fast are they going? Use your go-to equation. V is equal to lambda f, wavelength times frequency. Wavelength's 400 meters, frequency is 10 hertz. Multiply them together, 4,000 meters per second. Even the units turn out right. And if you're careful, you realize that the wavelength is meters per cycle, and hertz is cycles per second. The cycles cancel out. So even though we don't usually put the cycles in there, they do properly cancel out, and you do get the right units for your answer. Okay, next thing, take the same seismic waves and pass them through a place where the speed of the waves is a third of what it was in the solid rock. How much does the frequency change? Okay, pause it if you need to think about getting an answer. Okay, here's the answer. You're changing the medium, so the wave speed changes. Frequency is due to the source, not the medium, so the frequency can't change. Wavelength will, not the frequency. Remember, the wavelength is what results from the wave speed, material, and the frequency, the source. So if that was a trick question, be prepared for more like that later on. Okay, now we've got to get the wavelengths. How much does the wavelength change, right? So, okay, if the speed is a third what it was before, that's the left-hand side is now a third, and that's equal to the new wavelength times the same old frequency. So the new wavelength better be a third of the old one, so that the equation still works. And that's what it is. And now we think about a radio station broadcasts at 100.7 megahertz. What is the wavelength? And if you think about it for a little minute here, you might realize, hey, wait a minute. What about speed? We need speed to do this, right? Because we want to use our speed is equal to wavelength times frequency. And then you realize something, right? Radio station. What does that mean? That means electromagnetic waves. Electromagnetic waves travel at the speed of light. Speed of light is one of these things I think we mentioned at the very beginning of the semester. 299792458 meters per second. Something worth remembering because there's a nice ring to it. Or you can just use 3 times 10 to the 8 meters per second. So speed is 3 times 10 to the 8 meters per second. It's equal to the wavelength times the frequency. The frequency is here. Divide both sides by the frequency. 299792458 divided by 100.7 times 10 to the 6 hertz cycles per second. And you end up with meters per cycle of 2.98. And notice how cycle has been dropped. That's typical. Be prepared for that, as I warned you before. Okay, now what about the wave behavior here? What happens when two waves meet each other? Most of the time, in what we call linear media, but most of the time what we do in this class, waves that travel to each other won't really affect each other at all. They'll just add up. We call this interference. And we'll do that later in the semester. So where one is positive and the other is positive, they'll be bigger. Where one is positive and the other is negative, it'll be smaller. Where one's something and the other is zero, it will be the something. And after they overlap, they'll just go off looking like they did when they came in. And when a wave encounters a boundary, part of the wave is reflected. We already saw something about this when I was doing our slinky experiment. If the boundary holds the medium fixed, it's inverted. If the boundary allows the medium to move freely, it is not inverted. And so that is the, that's what you saw in the demonstration. And that's the big thing you have to remember about this. And so that's it. That's all we have in 16E for today. And so I will see you next time.